Welcome back. In our previous example, we tried to select a power plant by estimating the power required by the system during this climb. So, in this, while estimating this, what we assumed is the density during this climb remains constant, which we considered as sea level density, which is 1.225 meter cube. So, let us repeat the same exercise by considering density at 1 kilometer altitude, right, and see what is the difference in the power requirement. Now, when you select a power plant, you need to select based upon the maximum requirement. Let us see which of these is going to have the maximum requirement, either at sea level or at 1 kilometer altitude. Now, what we have from yesterday, we figured out the rate of climb as, for this particular case, is 5.5 meters per second, which is the vertical velocity of climb. And since we need to fly at 20 meters per second, what we have, V infinity sine gamma, this rate of climb, is equals to 5.5. Gamma is sine inverse 5.5 divided by 20 meters per second, which is approximately 16 degrees. Right. Gamma is 16 degrees here. So, from equations of climb 1 and climb 2, CL1 and CL2, what we have, so T minus D is equals to W sine gamma, right. So, rate of climb is equals to power available minus power required divided by weight. This implies the power available, the power that the engine has to deliver is equals to rate of climb times the weight of the system plus power required. This is density into corresponding velocity of climb. So, the rate of climb here is 5.5. We need to figure out what is the D and what should be the drag here. If you know that, then we will be able to estimate the corresponding power that has to be delivered from the power plant. So, rate of climb into W plus half rho V infinity square S, so it will be V infinity cube S into CD naught plus K into CL square. We have CD naught and K from here, right. So, now we need to figure out what is the density at 1 kilometer altitude. So, to do that, let us recall our standard atmosphere. First, we will try to convert the geometric altitude to geopotential altitude, R into Hg by R plus Hg, where R is radius of Earth, approximately 6400 kilometers, right. So, from here, for 1 kilometer altitude, it will be approximately 999.8 meters, which is almost equivalent to Hg, right. So, it's not going to make much of a difference. Now, I have rho 2 by rho 1, or rho at a altitude divided by rho at sea level is equals to T at an altitude by sea level temperature raised to the power of minus G naught by AR minus 1, right, where G naught is 9.81 meters per second square and A is minus 6.5 Kelvin per kilometer and R is 287 joule per kg Kelvin. It's a universal gas constant, right. this equals to rho naught into, what is rho naught? Rho naught is 1.225 kg per meter cube, right? So, how to find T? We know from the definition of lapse rate, which is A is equals to dh by dt, dt by dh. So, T2 is equals to T1 plus A into H2 minus H1 for a gradient layer. So, A is minus 6.5 for the first gradient layer, right? Now, what is rho is 1.225 into T1 plus A into H2 minus H1 divided by T naught in this case minus G naught by AR minus 1. So, if you solve this, the density at 1 kilometer, it turns out to be 1.116 kg per meter cube. Now, substituting this density in this equation, (5.5 meters per second into 3.5 kg multiplied by 9.81 to convert this into newtons, and half into what is the density here, 1.116 into 20 cube into 0.787 multiplied by 0.35 plus 0.16 CL square. So, for the same flight condition, we need to find out the corresponding CL values here, right? So, the CL for this condition is, we have L is equals to W cos gamma from CL2, equation CL2, right? So, what is CL? It's twice the wing loading into cos gamma divided by density at 1 kilometer. We have to use at 1 kilometer altitude into V infinity square. Right. So, this turns out to be 0.187. Right. Let me just check. The CL is 0.1877. This is the CL for this case. Now, substitute this CL here in this equation to figure out what is the corresponding power requirement from the power plant, right? Just substitute that, it will be 331.47 watts. Right? Now, what is the shaft power required to achieve this flight conditions? This is power actually required by the system, entire system, divided by propeller efficiency. This is 331.47 divided by 0.85 is approximately 389.97 watts. Right, this is the shaft power that is required at 1 kilometer altitude. Right, this is the power requirement from the system. So, when we calculated the same shaft power at sea level, what we This is 401.81. So you have to consider the highest shaft power that is required, right? Then you have to use this shaft power to select the corresponding power plant by a factor of safety. Right? So till now we assume that the weight of the aircraft is given or the UAV is given, but for a designer it is never an input. Weight is never an input. You have to estimate the weight of the system. So in order to estimate the weight, we need to understand the total weight, how this total weight of the system is summed up, right? What are the components that are contributing towards this total weight? What are the major components? Now let us look at weight estimation. Right. So what does this weight estimation depends upon? Why it varies from one aircraft to the other aircraft or one UAV to the other UAV? Okay. So there is something called mission requirements. Right. So this weight of a system varies from one aircraft to the other aircraft or one UAV to the other UAV based upon the mission requirements. Mission requirement or set of the tasks that this aircraft has to perform or the set of performance parameters that this aircraft has to possess, right? So what will be a typical mission requirement of a UAV? Say, again going back to the profile, right, mission profile. So it has to climb to a certain altitude, either it has to cruise to a different location and land, right? So again, climb, and in some cases you also have takeoff, right? There is something also called takeoff, climb, cruise, descent, or glide, you can say, landing, approach and land, right? So this is one such profile what this UAV has to perform, mission profile what this UAV has to perform. And here in this cruise, so although you have two UAVs which are performing the similar type of mission profile, the weight can vary, right? So this entirely depends upon the cruise as well as the weight it has to carry. So what do you have in a UAV in the first place? We are talking about fixed wing UAV, right? Okay. So what we have is wing, tail, fuselage, right? All these things sums up to structure, right? And we have a engine or a power plant, right? So this is a propulsion system. What is the purpose of any UAV? Of course, it is definitely not going to carry passengers, but it is designed to perform a task which involves either sensing or taking payload from one location or taking certain cargo from one location to the other location, right? So either sensors and all these things are considered as payloads, right? So there will be payload, right? At the same time, you have a power plant here, and this power plant has to be, so where do this energy I mean, how this power plant is running. There should be a onboard energy storage, right? So energy supply. So this can be broadly considered this way. Of course, there will be avionics, right, which will be a smaller percentage compared to all these things, and you can sum it up to either of this, either structure or propulsion part, right. So the total weight of this UAV is contributed from structure, power plant or propulsion system, and payload. Same time you have energy supply. In some cases it is fuel or battery, right, either fuel or battery. Now, why this weight changes from UAV to UAV? It may have to carry different payloads, right. A smaller UAV may supposed to carry a smaller camera, which may weigh up to 250 grams, right, and it can be used for a surveillance purpose with a 1 hour endurance, right. So as the requirement changes, the weight changes, weight of the system changes, right. So there can be a heroine class UAV where it's of 2000 kg class, where the structural weight the structure has to be designed accordingly, right, whatever the payload that he has to carry, and that can't be compared with the weight of a 5 kg UAV, right. The structural weight of a 2000 kg UAV cannot be compared with a 5 kg UAV, right. It will altogether a different story further. Now, how to start with the weight estimation, right. So we broadly understood that these are the major components that contributes towards the total weight of the system, right. How to start with this? How to start estimating these weights? If I know the individual components, then I'll get to know what is the total weight. That's the whole idea, right. Now, payload is one thing which is given as an input, right, that comes from the mission requirements. So this is a known quantity. So unknown for this new design, before starting anything, the unknown for this new design will be what is the structural weight, what is the propulsion weight, and what is the fuel weight ratio, right. Now, how to start this? Let us say W is a total weight. Can I write this as W or W takeoff or maximum takeoff weight or takeoff weight, whatever it is, right, into W takeoff plus W propulsion system W payload plus, so let me represent payload as PL, propulsion, ST structures, PR stands for propulsion, PL stands for payload, and weight of the fuel. So let us initially talk about the fuel powered UAV, right. So the energy is supplied to this power plant is by means of fuel, right. So this is W take. So where WTO is equivalent to WMTOW, maximum takeoff weight, MTOW is a maximum take off or takeoff weight, simply takeoff weight. ST stands for structural weight ratio, ST by WTO. WPR by WTO stands for propulsion weight ratio. WPL stands for payload weight of payload. Fuel weight ratio. Right? So let us consider this equation as W1. Let this be weight estimation 1, WE1. This as WE2. Okay. Now let us rewrite this WE2. Right. So W takeoff into 1 minus W structural weight to W overall takeoff weight minus W propulsion weight to W takeoff and fuel weight ratio here minus fuel weight ratio is equals to, or is the, what we left with the right hand side is a payload, weight of the payload. This implies W takeoff is equals to W payload over 1 minus structural weight fraction subtracted by propulsion weight fraction and then minus fuel weight fraction. So if you know these values, the structural weight ratio, propulsion weight ratio and fuel weight ratio, you will be able to, since payload will be given as an input there, you will be able to figure out what is the overall takeoff weight. Right? So why we call this as estimate here? Why it's an estimation? There should be some meaning, right? Because we are not actually calculating, we are trying to estimate based upon the historical data here. Right? So the structural to takeoff weight ratio, we consider this from the historical data of the aircrafts which are designed to perform this similar mission. Right? At the same time, propulsion weight ratio we'll also figure out it from the historical database of the UAVs which are designed to perform the similar mission requirements. Right? And then when you are doing this, like when you are trying to estimate and when considering by considering the values of previous UAVs, what is the new with this WTO? What is the new with this particular UAV that you are going to design? So this fuel weight ratio will vary. Okay, if you are designing a UAV based upon this IC engine, which has where fuel is the energy that is supplied to the system, right? So if you are designing that UAV, so this fuel consumption or the ratio changes based upon your particular mission requirement, this particular mission requirements, right? So say if you want to, so your previous UAVs may be doing a 1 hour cruise or 2 hour cruise, so your UAV may, the one that you are going to design may have to perform a 5 hours endurance, right? Or should be capable of traveling 500 kilometers instead of 200 kilometers. Let us say if 200 is the range of previous UAVs, right? So this factor initially is going to affect this W takeoff weight, right? Now once you know what is the takeoff weight for the initial iteration, right, then you will be able to figure out, once you know the takeoff weight, you will be able to find out what is the corresponding power requirement, right? If you know the power requirement,
for various phases based upon the mission requirement, right, you need to say if this is a typical mission, you need to know what is the power requirement during climb, during cruise, during takeoff, right. So takeoff, it will be very minimal here anyways, right. So if you know the power requirement, you will be able to select the corresponding power plant. Once you have the power plant, you have an accurate value of this WPR here of the propulsion system, right. You have a accurate value here. Now you need to figure out what is the structural weight based upon this. Once you have the accurate value of this propulsion power plant, then you will be able to, then you have to again iterate this step, iterate the process, and you have to update the fuel weight again. Once you have these two, then you will be able to find out what is the structural weight, because you will be designing the structure, right. So once you have all these values, you are actually bringing this equation to the particular UAV that you are going to design, right. So you have started with the data of the previous UAVs, but right now you are trying to adapt this equation to your particular design, right. Let us do this step by step, right. First, we need to understand what is this weight ratios. What are these weight ratios? So let us segment this mission profile. So the starting of takeoff is, consider this as 1, and the starting of climb, consider this as 2, and the starting point of this cruise consider is 3, and the end of cruise is 4, and say 5 is the starting of landing, and finally 6, this point 6 is a, what do you call, once you landed and end of the mission. Okay. So how much time do you think takeoff require? So in our first introductory lecture, we saw a flying wing, right? Flight of a flying wing, where there is no takeoff. We just launched hand launch system, right? So we can at max consider a takeoff of 30 seconds or half a minute, right? So climb maybe 3 minutes or 2 minutes, 2 to 3 minutes. Whereas cruise can range from anything between 60 minutes to or 1 hour to say 10 hours, 24 hours, right? It depends. Right? And descent, again it may take 2 to 3 minutes. Generally it will be a gliding flight, glide. So where the fuel consumption is very, very minimal, right? And once you landed, then it may take around say half a minute, again 30 seconds or 0.5 minute. So that's a 0.5 minute. This is also about 0.5 minute. So now it is clear that the fuel consumption is maximum during cruise, right? That means if you look at the fraction, W4 by W3 will be higher compared to W3 by W2 and W2 by W1, right? At the same time, W5 by W4 and W6 by W5. So we need to figure out this fuel load that need to be carried in order to perform this particular task, which is either cruise or loiter, and a combination of that, right? At some applications may need only loiter around the launch point, right? Surveillance about the launch point. In some applications, you have to reach to a particular destination and then perform a surveillance there, right? So it may involve both cruise and loiter. So the major time that is spent here is for cruise as well as the loiter, right? Loiter is, see, you have to reach a particular destination and perform a loitering and may come back to the home, right? So cruise
loiter, climb, take off.
So major time of this mission is spent in performing cruise and loiter missions, right? So we need to figure out what is the fuel loads for this cruise and loiter. At the same time, let us also look from the historical database what is the fuel ratios for various mission segments. Right?
So serial number, let us say mission segments and weight fractions. So let us say first say taxi and takeoff.
So you can't lift a 800 kg UAV. Definitely from your hangar you have to take it to the runway. So you need to do a taxi. At the same time you need to take off from the launch point, right?
So typical value of this is 0.98, right?
So this is from the historical database of 150 aircrafts, right? 150 UAVs.
So the second one,
Yeah, 150 or 130 to 150 UAVs, right?
and the second one is
Climb.
so the third one is
See, descent. So we can't comment much about this cruise because if for each and every UAV the mission is different. You can't compare it.
right. The fourth one is landing, approach and landing. Right.
So typical values of this are
This is 0.97, this is 0.98, this is 0.998.
This is 0.99, I'm sorry. So these values are from historical database. See, if you look at this, it is almost equal to 1, that is W3 by, say, in this case, W2 by W1 is almost equal to 1. Compared to overall takeoff weight, the fuel weight consumed is very, very less. Right. Similarly, you can see for the climb it is also 0.97, and for descent it is 0.99, and approach and landing it is 0.99. Right. So here it is almost more closer to 1, right? So the major difference for each and every design will come due to the cruise and loiter. That is a major segment of your mission, right? Now let us estimate this loads for this fuel loads for this particular segment, cruise and loiter, right? Say, what is this fuel weight? What do you think is the fuel weight for any aircraft? Let us say a fuel powered aircraft. So what do you think is the fuel weight here? So you have W1 and W6. So the difference between W1 and W6 is the fuel weight. Don't you think so?
W1 minus W6. What is the fuel weight?
Fuel weight is WF is equals to W1 minus W6, where W1 is the maximum takeoff weight and W6 is after landing, right? So during this entire process, whatever the fuel that has been consumed will be WF. Right. This is straightforward. So WF is equals to W1 into 1 minus W6 by W1, right, where W1 is a takeoff weight, am I correct? So to estimate this WF by W takeoff, we need to find out what is the weight ratio of W6 by W1. Since we have segmented this mission profile, we can express this W6 by W1 as, I'll erase this part. This is this equation, name it as WE3, and this equation is WE4, weight estimation equation 4, and this is weight estimation equation 5, right. So what is this W6 by W1? So we have various segments here, right, which see the climb dynamics is completely different to takeoff dynamics. That means the fuel consumption or the power requirements are different and the fuel consumption is different here. Whereas in cruise, again the dynamics compared to climb and descent are completely different, and so the fuel consumption, right. So since each segment has different dynamics and different fuel consumption, right, so we can express this as W2 by W1 into W3 by W2 into W4 by W3 into W5 by W4 into W6 by W5. Am I correct? Am I correct? This one. One to 5. Right? So in this case it is we just witnessed like from the table with the historical database, we looked at like what is W2 by W1, W3 by W2 and W5 by W4 and W6 by W4. So this particular weight ratio belongs to descent, which is almost 0.99, right. This corresponds to landing phase, which is 0.998, so this is for cruise. So to start with the initial estimate, the unknown is this cruise part, right? Why? Because so these things can be compared with the, can be considered from the historical database. This corresponds to the climb phase, and it is approximately 0.97, and this is again 0.98. Takeoff phase, which is 0.98. So your new design will vary because the fuel weight ratio of your new design will majorly differ with the previous design because of this cruise and loiter phase, this W4 by W3 phase, right. Now how to figure out this W4 by W3 phase? Now let us look at something called range and endurance or loiter. So let us confine ourselves to this propeller driven aircrafts, right, because we are not going to, we don't see generally a jet driven unmanned system, right. So let us look at the propeller driven system here. And why range and endurance? It talks about the distance that you can travel with a given load of fuel, right? That means you'll be able to figure out the fuel load to travel a particular distance, because cruise we say 1 hour or 10 hours, right, or so many kilometers. So when you mention that from this mission requirements, that means you are specifying either range or endurance of the system, right? So once you know the range, what should be the corresponding fuel load that you need to carry to perform this particular task, right? So let us define, since we are talking about IC engines, right, or a propeller driven engine. So let us consider this fuel powered IC engine. Fuel powered IC engine. So the output that you get is, actual output will be this shaft power. Whatever the output that you have from this is a shaft power, and you use a propeller to convert this to useful power, right? Power available from the system, which is the useful power that accelerates your aircraft or provides the required velocity for this UAV, right? Now let's have a look at it. It's worth showing this IC engine. It's a small IC engine, right? So this is a carburetor that controls the fuel air mixture, and there is a valve inside with which you can control this fuel air mixture and the corresponding RPM, right, and the shaft power. So what is shaft power here? The power that is available along this shaft, right? So it is this is a mechanical power that will be available by, so this is a fuel inlet. The valve that you can see here is a fuel inlet, right? So whatever the fuel that is going to use to generate this power, right? So in other words, what is the amount of fuel that is consumed to produce a unit of power, right? So that is defined as specific fuel consumption, right? Specific fuel consumption for this IC engine is CP, which is defined as weight of the fuel consumed in producing unit power. So what are the units of this? Newton per watt hour. Newton per watt hour. Right? This is for IC engine. So see, this shaft power is converted to useful power by means of this propeller. By means of, we are using a combination of propeller with this IC engine to convert this mechanical power to the useful power, right? So the power that is available, the specific fuel consumption is defined with respect to this shaft power, right? We know the useful power to us is the propeller efficiency times this shaft power, right? This is the propeller efficiency. How efficient this propeller is going to convert this available mechanical power to the useful power for us, right? So we can also look at this electric powered systems, right? This is a brushless motor. It's an outrunner brushless motor, and there is a propeller combination here. So for this IC engine, fuel is given as an input, right? For propeller based electric based system, we use battery power as an input to this brushless motor, right? And again here the output will be a shaft power. In either the case, the output is a mechanical power. By means of this propeller, we convert it into the useful power, right? Useful power for UAV, right? So this is typically a 1100 kV motor, right? Which means it rotates at 1100 it has an RPM of 1100 per volt, right? So when you are operating this with 4-cell battery, which is approximately 12 volts, right? So you have to multiply the corresponding RPM, right? And that's a maximum kV, right? And it will deliver a thrust of 2 kgs, right? When operated using a 12 volts battery. And there is also a ducted fan, right, which is also powered by electricity. Like we use onboard battery to power this particular power plant. And so you can see here there is a fan, right? So the output again here is a shaft power. See, this is the back side of this particular EDF. We call it as electric ducted fan, right? So the output is a shaft power here. It has a similar concept of this outrunner motor, brushless outrunner motor. So the only thing is here to minimize the propeller diameter, right? We use fan, right? A series of fans here. Series, or here it is a single fan with multiple blades, right? So this is going to deliver you this fan is going to convert the available mechanical power to the useful power, right? So in all the cases we need to multiply the available shaft power with the efficiency. So by the way, this particular EDF delivers a 4.5 kg thrust with a 6S battery, which is approximately 24 volts, is an input voltage to this. And you can control the speed by means of speed controller. Like we'll discuss about these things in the later lectures. And one more announcement that I would like to make is, like most of the students were mistaken this course as an aero modeling course, right? Some of the students. So I kindly request you not to mix this course with the aero modeling course, right? And we are talking about design. No? Design, when you say it is a 3-dimensional, I mean either 3D CAD model that has to come as an output. So the 3D, when you say 3D CAD model, it has certain geometry with size, right? Wing size, fuselage size, what is the engine size or the engine capacity, and what is the tail size. So all these numbers we arrive by means of this dynamics, aircraft dynamics, right? With the help of flight stability, I mean both performance and stability control. We use those concepts, and moreover aircraft design or a UAV design is a synthesis of this performance and stability and control, right? Although you may not be learning new things here, but you will try to apply what you have learned in performance and stability and control course to design the flight vehicle, right? Of course, in one of these lectures we will try to show you how to build a UAV, but that's not the main motive of this particular course, right? So coming back to this, like whatever the shaft power available either from the fuel based or the electric based engine, it has to be multiplied by the efficiency factor of the propeller or the ducted or the fan, right, to get the available power, right? So now the power available is a propeller efficiency times shaft power, and we have defined something called specific fuel consumption of this propeller based engine, right? So specific fuel consumption here is equals to the amount of fuel consumed to produce unit power, right? What happens to a jet engine? Of course, we will not be talking much about jet engines, but we need to define specific fuel consumption. Is a thrust specific fuel consumption is defined as weight of the fuel consumed in producing unit thrust. So units are Newton per Newton, right? So this is the thrust specific fuel consumption. This is specific fuel consumption. Now, since we are talking about cruise, range is like what is the distance that you travel in the during cruise, right? Even endurance for that case is the same. We will talk about cruise,
both these parameters talks about cruise, which means you have constant velocity, which is the distance traveled over particular time, right? So this dx is equals to v infinity into dt, right? Okay, so dx is v infinity into dt, and and if I integrate this from 0 to r range, which happens over a time t1 to t2, right? So this is v infinity into dt, right? So this integration is the range r, so t1 to t2 v infinity dt. Again, we need to discuss what is. Okay, let us go back to this weight again. Let us look at this weight. Say, what is weight of the fuel, or total weight of this aircraft is equals to weight of the fuel plus total weight other than fuel, right? Do you accept this? So total weight of the aircraft is equals to weight of the fuel plus weight of the aircraft minus fuel. Okay. So this may include payload. See, empty. We can't say it as empty weight, right? So it may also include payload and WS is the fuel weight. So now say the change in the total aircraft weight is the change due to fuel consumption, because this is going to remain constant. This is d by dt of Wf, which is W dot F, right? So this d by dt is W dot of the aircraft is the W dot of the fuel, right? Do you accept this? Okay. Now, what is W dot F here? For a propeller engine, W dot F is equals to, or dW by dt is equals to Cp into PSH, right? Shaft power. What is shaft power? Shaft power is efficiency, propeller available power divided by efficiency of the propeller. So what is available power? Is a thrust into the velocity, right? It's a propeller efficiency. Okay. Now what is dt? dt is equals to eta of the propeller divided by Cp into T into V infinity, right? Into dWf. We just manipulated this equation. Okay. So you may consider this as this equation as W8, WE8, weight estimation 8. WE8. Okay.
So, now substitute this dt in this equation. Let us substitute the dt in this equation, range equation. So from T1 to T2, what you have is W at T1, say Wi, say Wi plus 1 at T2. Okay. So this is at the starting of this mission, which is T1, and the end of this particular segment of this mission. Right. So this is V infinity times eta of the propeller efficiency divided by Cp into T into V infinity into dW of the fuel. So don't you think this dW of the fuel is equals to dW of the aircraft? Cp into T into V infinity into dW. Since dW is equals to dWf, right? Yeah, we can change this to dW, right? Now let's integrate this. And what is the relation between Cp and C? We'll look into that. Once we finish this, we'll look into it.
Range is equals to integral Wi to Wi plus 1.
So again, small correction. So here the Cp is minus W dot of F divided by PSH. Right? You have to include minus here. So because the reduction in weight, so Wf is a reduction in weight, so it is negative. So Cp is a figure of merit. So it's like negative into negative, ultimately Cp becomes positive here. So Cp is defined as minus of Wf. Similarly, C is defined as minus W dot by T. Right? Please make a correction here. So the same will be reflected here, like substituting minus here,
minus of eta of the propeller by Cp into W by T into dW by W. This equals to minus Wi plus 1 to Wi, right, is equals to eta of propeller into Cp into
what is W by T? Since this is cruise, right?
what we have from C1 and C2. C1, C2, L is equals to W is C2 and T is equals to D. So W by T is L by D. So I can substitute L by D in this equation. This equals to, so this is L by D into dW by W,
Right? Okay.
so this is W of I plus 1 to Wi. R is equals to
Eta P and Cp remains constant, right, throughout the flight, and then L by D, since it's a cruise, you'll be flying at a constant L by D here, right?
and what you have is dW by W. This equals eta of the propeller by Cp into L by D into ln of W I by W I plus 1,
Right? So for a given fuel load and the weight of this aircraft, you will be able to, and if you know the L by D of your flight, you will be able to have a range R, right? Yeah. So if you want the maximum range, so finally range is equals to
eta P by Cp into L by D into ln of Wi by Wi plus. So this is your range which can be used for weight estimation WE 8. This can be 9. This is our ninth equation for weight estimation. Now, if you want to maximize the range, you have to maximize the L by D. Right, L by D max will directly reflect in your range maximum. So, what is the condition for L by D maximum? So, CL has to be root over L by D max is, so R max you can have when your L by D is maximum. Right. So, when is L by D max? What is the condition for L by D max? So, L by D max is equals to 1 by root over 4k CD naught, right, where CL for L by D max is root over CD naught by k, and CD for L by D max is equals to 2 CD naught. Why is the profile drag? The induced drag is equals to profile drag in this case. So, if you substitute this, the range maximum will be eta p by Cp into 1 by root over 4k CD naught into ln of Wi by Wi plus 1. Right, this is the maximum range that you can obtain for a given fuel load. And the corresponding velocity for R max will be root over twice the wing loading by rho into root over k by CD naught to the power of 1 by 2 or 4th root over CD naught by k. Right. Now, coming back to this W39, what we are interested in is finding out the weight ratio Wi by Wi plus 1, right. So, or say Wi plus 1 by Wi, otherwise Wi by Wi plus 1 to start with is equals to e raised to the power of R into Cp by eta p into L by D, right. So, this is the weight fraction, then Wi plus 1 by Wi is equals to e raised to the power of minus range into Cp by eta p into L by D. So, this is your fuel weight ratio that you need to carry. So, this is your WE 10. So, if you want to have a range, right, as per your mission requirement, you need to carry this much fuel load. So, the assumption that you have to make here is what is your L by D of your flight, right, and what can be the propeller efficiency, as well as from the historical data you will get to know what is the Cp of this particular, Cp of the engine that is used for this particular weight class of vehicles, right.